Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's use triple integrals and cylindrical coordinates to find the volume enclosed between two spheres. In this example, one sphere is defined by the Cartesian equation where x squared plus y squared plus z minus 4 all squared is equal to 16 and shown in red, and the other defined by x squared plus y squared plus z squared is equal to 4 shown in blue. The blue sphere is centered at the origin with the upper hemisphere above the xy plane and the lower hemisphere below the xy plane. Both hemispheres of the red sphere sit above the xy plane, with the lower hemisphere tangential to it where z equals 0. Let's take a look at the spheres in 3D form using a graphing tool. So this is the red sphere in isolation, and with this, both upper and lower hemispheres are above the xy plane, with the lower hemisphere being tangential to it. And this is the blue sphere in isolation, with the upper hemisphere above the xy plane and the lower hemisphere below the xy plane. And if I put the two together, we get this structure where the two spheres intersect. And if I limit the structure to where the two intersect, we get this. And we want to find the volume within. Note the volume includes part of the upper hemisphere of the blue sphere and part of the lower hemisphere of the red sphere. Our first step in finding the enclosed volume is to convert the Cartesian equations of both spheres into cylindrical coordinates. And so beginning with the blue sphere, whose Cartesian equation is z squared plus x squared plus y squared is equal to 4, we need to convert the x, y's and z's to r, theta and z. And the way we do that is we substitute r cos theta for x, r sin theta for y, and z remains the same, so z equals z. And after making the substitution, we get z squared is equal to 4 minus r squared into the bracket of cos squared theta plus sin squared theta. And using the trig substitution where cos squared theta plus sin squared theta is equal to 1, we have z squared equals 4 minus r squared. And if we take the positive square root of both sides of the equation, because the enclosed volume only includes the upper hemisphere of the blue sphere, we arrive at z is equal to the square root of 4 minus r squared. We now need to repeat this process for the red sphere, whose Cartesian equation is x squared plus y squared plus z minus 4 all squared is equal to 16. And after making the substitution, we arrive at z minus 4 all squared is equal to 16 minus r squared into the bracket of cos squared theta plus sin squared theta. And using the trig identity where cos squared theta plus sin squared theta is equal to 1, we have z minus 4 all squared is equal to 16 minus r squared. And taking the square root of both sides of the equation, we have z minus 4 is equal to minus the square root of 16 minus r squared. Note here we're using the negative square root, as the volume we're interested in falls in the lower hemisphere of the red sphere. And therefore z is equal to 4 minus the square root of 16 minus r squared. To find the enclosed volume, we need to integrate over the region, which we'll call E, and some infinitesimally small pieces of volume shown here as dv. We need to unpack this and define our region using cylindrical coordinates. This will give us our limits of integration for r, theta and z, and then look at what dv equates to in this context. So let's begin with the limits of integration along the z-axis. To help with this, let's limit our structure to show the region of intersection. The best way to think about this is that we are summing infinitesimally small pieces of volume along the z-axis between a function that defines the upper bound and one that defines the lower bound. So as we can see from this diagram, the structure is from the upper part of the blue sphere and the lower part of the red sphere. The lower limit of integration is therefore the function of the red sphere, where z is equal to 4 minus the square root of 16 minus r squared. And the upper limit of integration is the function of the blue sphere, where z is equal to the square root of 4 minus r squared. Moving on to the limits of integration for r, they can be found where the two spheres intersect. At this point, a circle is formed, and we can equate the equations of the two spheres in cylindrical coordinates to find the value of r. So equating the two, we have the square root of 4 minus r squared is equal to 4 minus the square root of 16 minus r squared. If we square both sides of the equation, we get 4 minus r squared is equal to 16 plus 16 minus r squared minus 8 multiplied by the square root of 16 minus r squared. And simplifying this, we can see r squared here cancels with r squared here. Simplifying this further, we get the square root of 16 minus r squared is equal to 7 divided by 2. Squaring both sides of this equation gives 16 minus r squared is equal to 49 divided by 4. And solving for r, where we take the positive square root, we get r is equal to the square root of 15 divided by 2. The upper limit of integration for r is the radius of the circle, so where r is equal to the square root of 15 divided by 2. And as r begins at the origin of the circle, the lower limit of integration is where r equals 0. And to find the limits of integration for theta, we need to look at the coverage as r rotates counterclockwise around the circle. As we can see, r goes full circle and therefore rotates the full 2 pi radians or 360 degrees. So the lower limit of theta, where theta starts, is at 0, and the upper limit of integration is where theta finishes, and in this case it's 2 pi radians. Now that we've defined our region using the limits of integration, let's now unpack what we are integrating. So in our case, dv. So dv represents infinitesimally small pieces of volume. We're using triple integrals to sum each of these to get the total volume. Let's look at the dimensions of one of these. If we look at the green shaded region, this represents an infinitesimally small piece of volume dv. We can think of this as a tiny rectangular box where the volume is given by the height multiplied by the width multiplied by the length. So let's apply this to the green shaded region. We can see that the height is along the z-axis, and it's an infinitesimally small piece of z represented by dz. The width of the box lies along the radial distance r and is an infinitesimally small piece of r represented by dr. And the length lies along the arc of the circle and is infinitesimally small. Now the arc length of a circle is given by the radius multiplied by the central angle theta. In this case, theta is infinitesimally small, represented by d theta. If we now put all these infinitesimally small dimensions together, we see that the volume dv is given by dz rdr d theta. And we sum all these pieces of volume using our triple integrals to get the total volume. So we now have our triple integral where we're integrating dz rdr d theta. So let's begin the evaluation process, beginning with the integral for z. So we want to integrate from z equals 4 minus the square root of 16 minus r squared to z equals the square root of 4 minus r squared dz. And using the power rule to evaluate this, it evaluates to z. Plugging in the limits of integration, we have the square root of 4 minus r squared plus the square root of 16 minus r squared minus 4. And so for the middle integral, where we integrate over r, we now have 3 separate integrals, and we'll evaluate these one by one. And beginning with the easier of the 3 of these integrals, we want to integrate from r equals 0 to r equals the square root of 15 over 2 minus 4r dr. And using the power rule to evaluate this, we get minus 2r squared. And plugging in the limits of integration, we get a final answer of minus 15 divided by 2. And for the middle of the 3 integrals, we want to integrate r equals 0 to r equals the square root of 15 divided by 2, r multiplied by the square root of 16 minus r squared dr. And to do this one, we need to make a substitution. So we're going to let u equal 16 minus r squared. So du by dr is equal to minus 2r, and minus du over 2 is equal to r dr. And now that we've made a substitution for r, we can change the limits. So the upper limit of u is 16 minus 15 divided by 4, and this equals 49 divided by 4. And the lower limit is where u equals 16. So now if we make the substitution and add the new limits, we have minus 1/2 multiplied by the integral from 16 to 49 divided by 4 of u to the power of 1/2 du. And using the power rule to evaluate this, we're left with minus 1/3 multiplied by u to the power of 3 over 2. And if we plug in the limits of integration, we get a final answer of 169 over 24. And for the last of the 3 integrals, we want to integrate from r equals 0 to r equals the square root of 15 divided by 2, r multiplied by the square root of 4 minus r squared dr. And to do this, we're going to make a substitution. So we're going to make u equal 4 minus r squared. Du by dr is equal to minus 2r, and minus du over 2 is equal to r dr. And at the same time, we're going to change the limit of integration. So the upper limit of integration becomes u is equal to 4 minus 15 divided by 4, which is equal to 1/4. And the lower limit of integration becomes u equals 4. And now if we make the substitution and add the new limits, we have minus 1/2 multiplied by the integral from 4 to 1/4 of u to the power of 1/2 du. And evaluating this using the power rule, we have minus 1/3 multiplied by u to the power of 3 over 2. And plugging in the limits of integration gives us a final result of 21 divided by 8. If we now sum the results of all 3 integrals, so that's 21 over 8 plus 169 over 24 minus 15 divided by 2, we get a result of 13 divided by 6, which gives us our outer integral, where we want to integrate from theta equals 0 to theta equals 2 pi 13 over 6 d theta. And using the power rule to evaluate this, we get 13 over 6 multiplied by theta, and plugging in the limits of integration gives us a final answer of 13 pi divided by 3, and is the volume enclosed between the 2 spheres.